Hi everyone. In the last few lectures, we discussed pairwise sequence alignment, where we aligned two genetic sequences in order to find out how similar they were. In this lecture, we are going to extend on the pairwise sequence alignment and talk about how we can align more than two sequences and what sort of additional information that may give us. When we performed pairwise alignment, we made a number of assumptions and decisions. We had to choose a gap penalty model along with values for gap penalties. We had to choose a substitution matrix that dictated how favorable aligning two residues was. All of these decisions affect how an alignment is scored and how we define the best alignment. When we look at a pairwise alignment, we need to understand that even though it is optimal in the sense that it has the highest possible score, it may not be biologically the most accurate alignment. The residues that are matched up may not really be the same residues corresponding to the residues in a common ancestral gene. Multiple sequence alignment provides a greater evidence than pairwise alignment. If we look at 100 sequences and see the same identical residues line up, we would have a higher confidence that those residues are genuinely related to each other. Multiple alignment is considered to be more accurate than pairwise alignment, which means we can use a multiple alignment to go back and correct the mistakes in a pairwise alignment. After you construct a multiple alignment, you can extract conservation information about individual residues or a stretch of residues. This gives insight about how important those residues are for the function of the genes. Especially for proteins, such information is critical for making predictions about the structure and interactions of proteins. Formally, multiple sequence alignment is defined as taking a number of sequences and lining up their residues such that identical or similar residues end up in the same column. Each sequence is kept intact, but gaps are introduced to shift the residues within each sequence in order to maximize the similarity of the residues in a column. Just as in pairwise similarity, we need to capture the similarity of the residues as a score. The score of the entire alignment is calculated as the sum of the scores of each column. Let's take this column as an example. The score for that column is the sum of the scores of all pairs of residues. Substitution scores are symmetric. So if we add the score of VA, we don't need to add the score of AV. The total alignment of the entire multiple alignment is then calculated as the sum of the scores for each column. There is an alternative calculation that will result in the same total value. Instead of looking at each column, we look at each pair of sequences and calculate its pairwise alignment score. Here you see the pairwise alignment score of aligning the proteins A and B. The total alignment score is then the sum of all pairs of pairwise alignments. While looking at all pairs, which is what we just demonstrated, is the most common method for the alignment score, there are other formulations that may save computational time or be more biologically relevant. In the star method, a central sequence is selected and the total score is calculated as the sum of the pairwise scores with that central sequence. In the phylogenetic tree method, a tree that represents the evolutionary history of the sequences is used. This approach better represents the evolutionary events that gave rise to the sequences. Even though phylogenetic tree is theoretically more accurate, the problem with the phylogenetic tree is that constructing an accurate tree is a challenging problem in itself. Just like in the pairwise alignment problem, settling on a method for calculating the alignment score is not sufficient. We need to come up with a method that will find the multiple alignment that results in the highest possible score. It turns out that we can use the same dynamic programming algorithm to solve the multiple sequence alignment problem, but the computational complexity is going to be much higher. Let's demonstrate this for aligning these three sequences. In order to find the alignment with the highest score, we need to consider what the last column of such an alignment could be. There are only 7 options for the last column of an alignment of 3 sequences. For each of these 7 options, we'll assume that we somehow have already calculated the best score of aligning everything up to that point. Since the alignment score is additive, the total alignment score for each of these options can be calculated as the alignment score up to that point plus the score of the last column. After we evaluate each of these 7 options, we would then pick the highest scoring one to be our multiple sequence alignment. And again, like what we did in the dynamic programming for the pairwise sequence alignment, we would start with small prefixes of these 3 sequences and follow this strategy of considering 7 options and picking the best one and build our way up to the alignment containing the full-length sequences. In pairwise alignment, we had 2 sequences and we used a 2-dimensional dynamic programming table to find the best scoring alignment. With 3 sequences, we would need to build a 3-dimensional cubical structure where each little cube would represent the alignment of prefixes from the 3 sequences. To find the best alignment of 3 sequence prefixes of length I, j, k, the 7 options will correspond to coming to that entry from one of the previously calculated scores. For example, coming down along this edge would correspond to having A in the first sequence align with gaps in the other 2 sequences. Coming diagonally across this face would correspond to aligning A and T from the first and third sequences and having a gap in the second sequence. Coming from the main diagonal would correspond to aligning the residues A, G, T from the 3 sequences. This all sounds fine, but let's see how much time this process would take us. Let's imagine that on your final exam, I asked you to find the best alignment of 3 sequences, each with 10 residues. You would have to fill in every little cube in your 3-dimensional dynamic programming table. You have 10 times 10 times 10, which equals 1000 such little cubes. For each little cube, you will need to calculate 7 options and pick the best one. So that makes 7,000 score calculations. Let's say all this takes you 7 hours to complete. Now let's find out how long it would take you to align not 3 but 4 sequences. There are 10,000 sub-alignments you will need to calculate, and for each one, you will need to consider 15 options for the last column of the alignment. So that would take you about 150 hours or around 6 days. If you try to align more sequences, the amount of time you will need to spend grows exponentially and the problem quickly gets out of hand. For example, for 10 sequences, you would have to spend about 1 million years to solve the problem. Even if you wrote a computer program to do the work for you, it will still be bound by the same time complexity. The computer will handle a few more sequences than you can, but the time it will need to solve the problem will still increase exponentially by the number of sequences and quickly become much more than you are willing to wait for. So we have a dynamic programming algorithm that is guaranteed to find the highest scoring alignment, but it takes too long. When the optimal solution to a problem takes too long, we typically try to come up with a faster method while sacrificing some accuracy. One such suboptimal method is to perform a progressive alignment, where we perform repeated pairwise alignments. At each step, we merge the closest pair of entries using pairwise alignment, and repeat these merge steps until we finally end up with a multiple alignment of all of the sequences. At each step, we may align two sequences, we may align a sequence to an existing alignment, or we can align two alignments. In order to make sure that the most similar sequences are aligned with each other first, we create a phylogenetic tree from the sequences and use this tree as a guide to dictate in which order the sequences will be merged. Each of the pairwise alignments can be solved using a two-dimensional dynamic programming table. The only difference from pairwise aligning two sequences is that now instead of having to align two single residues, we have two blocks of residues. The score of aligning these two blocks can be easily defined as the sum of all pairs of comparisons of residues from one block with the other. Let's take a look at the computational complexity of the pairwise alignment strategy for doing multiple alignments. Say we have k sequences and each one has n residues. Performing a single pairwise alignment would take n square amount of time. As we progress through the iterations, we will have slightly longer entries to align, but we'll ignore that. In order to build the phylogenetic tree, we need to compare each sequence with all the other sequences in order to find out how similar they are. That means we would perform in the order of k-square comparisons, each comparison taking n square time, so the total time of phylogenetic tree construction is k square n square. After we construct the phylogenetic tree, we keep merging sequences. If we have k sequences, we would have to perform k-1 merge operations until we end up with a single multiple alignment containing all the sequences. So that's an order of k alignments, each one taking n square, resulting in a total of kn square time. The overall time complexity of the progressive alignment algorithm is then k square n square for the phylogenetic tree construction and kn square for the merge operations. The term k square n square will dominate the time complexity, so we can just drop the kn square term, which gives us k square n square as the overall time complexity of the progressive multiple alignment algorithm. Unlike the full dynamic programming solution that was exponential in k, the time requirement for the progressive alignment does not grow exponentially. To give you an idea of how fast this grows compared to the full dynamic programming algorithm, let's say aligning 3 sequences, each with 10 residues, would take you about 1 hour to align using progressive alignment, compared to 7 hours you had to spend for the full dynamic programming. When you increase k to 10 sequences, you need to spend only 10 hours if you apply the progressive alignment, compared to 1 million years you had to spend for the full dynamic programming algorithm. I'd like to reiterate that progressive alignment is not guaranteed to find the best multiple alignment. One particular issue that progressive alignment suffers from is that mistakes made early on during the merge steps cannot be fixed later when you merge an additional sequence. For example, when we align ABA with BB, this alignment looks good enough. Once these two sequences were merged, they are locked in. We cannot later shift their residues around. When we merge another sequence to the alignment, we end up with a multiple alignment that is not optimal, because having BB here would have given us a better score. Making such mistakes is closely linked to the order in which we merge the sequences. For example, for the same set of three sequences, if we aligned ABA and ABB first and then merge BB to them, we would end up with a better alignment. Using the phylogenetic tree as a guide would help in this regard, but it still cannot guarantee that such mistakes will not occur. There are other methods that directly work on a multiple alignment and shift the gaps around to see if a better alignment can be obtained. I would like to introduce one such optimization method where we use a genetic algorithm to find a near optimal solution. Genetic algorithm is inspired from biological evolution. We maintain a population of solutions and evolve these solutions over many generations in order to improve them and find a better solution. Here, each individual in the population is a multiple alignment of the sequences, a possible solution to the multiple alignment problem. The alignment score of each of these possible solutions is used to define the fitness of that individual. We can start this process with a random initial population where each individual is a randomly constructed multiple alignment. The alignment scores may be low initially, but that is okay. It will improve over time. To move from one generation to the next, we make a selection of the fittest individuals. We randomly select individuals such that the ones with a higher score are more likely to be selected. We then take these selected individuals and modify them using mutations or combine them using crossovers. The mutation and crossover operations produce children which we collect into the next generation of the population. The mutation and crossover operations enrich the genetic pool of the population. When applying the genetic algorithm to a problem, you have to define how an individual is represented and how mutation and crossover operations are performed. For multiple alignment, we can just use the alignment as a matrix, where each row represents a sequence. In order to mutate an individual solution, you can take an existing gap in one of the sequences and move it around somewhere else within the same sequence. Or you can introduce a new gap in one of the sequences. Each new individual you create by mutations is going to be a valid solution. It may not be the best one, but it should still be a potential answer to the multiple alignment problem. Just because you are doing mutations doesn't mean you can take any residue and mutate it to a different character. If you change a character, you would be modifying the sequences you were supposed to align, and that would no longer be an answer to aligning the sequences you started with. The crossover operation is slightly more complicated. For crossover, we take two individuals from the population and combine them in the hope that we end up with a better alignment that has the best parts of the two parents. We pick a crossover point in one of the alignments, which is just a straight cut of the matrix. We then need to find where that crossover point is for each of the sequences in the second parent. Here we have cut the first sequence in the first parent after WGKV, and in the second parent, this is where the WGKV ends. In the first parent, we have cut the second sequence after WDKV, and here is WDKV in the second parent. We have cut the third sequence at WGKV, and here is WGKV in the second parent, and so on. We then take the first part of the first parent and the second part of the second parent and stitch them together to form the first offspring. The second parent will most likely not have a straight cut, so we would need to add gaps to fill in. Similarly, we create another offspring by combining the second part of the first parent and the first part of the second parent. We then calculate the alignment score of each offspring and keep the better of the two to carry on to the next generation. Mutations and crossover operations help the genetic algorithm survey and try out promising solutions. We would repeat the selection and the reproduction process for a pre-specified number of iterations, or until the solutions do not get any better, or until we find a solution that we are happy with. Genetic algorithms and other randomized search algorithms overcome the accuracy limitation of the progressive alignment strategy and produce better alignments with a modest increase in computational time. In summary, multiple sequence alignment results in biologically more accurate alignments than pairwise alignments. Multiple alignments are used to create sequence profiles which summarize a group of proteins and identify their conserved regions. Multiple alignment is a computationally difficult problem, and finding the optimal alignment is not feasible. Heuristic approaches have been developed to find near optimal alignments within practical computing times.